Good morning, everyone. Thank you so much for coming back from the coffee break. I'll be chairing this next session. And it's my great pleasure to introduce Andy Cooper. He is a man who needs no introduction, but he obtained his degree at Nottingham, I believe, then went on to UNC Chapel Hill, and then worked at Cambridge with Andrew Holmes. So that's something that we have in common together. And a secret fact is he was actually my PhD thesis examiner. I'm not sure if he remembers that. But anyway, he's done a lot of work on porous polymers, but today he'll be talking about his latest work related to robotics and AI. So thank you.
Thank you, Christine, and I do, of course, remember examining your thesis. And we can continue the examination later, if you like. So thank you to the organizing committee for the invitation. It's been a marvelous meeting so far. I've really enjoyed it. And I'm going to talk to you today about some of our work on robotics and AI. And I was looking through my slides, and I think there is less chemistry in this talk than any talk I've ever given. I'm asymptotically going to end up with zero chemistry at this rate. But I'm based in the Materials Innovation Factory in Liverpool, which is a center for robotics and automation. I'm not going to say too much about the MIF today, but just to say this actually built upon an earlier center called the Center for Materials Discovery, which opened in 2005. So we've been working on this automation topic for a long time, more than 20 years. In 2005, no one was talking about AI. We were calling this high throughput or combinatorial chemistry. But of course, a lot has changed in the world since 2005, and a couple of mega trends, which will be no surprise. I don't think I need to talk about AI as that mega trend, but this area is developing very fast, in a sort of scarily fast, actually. But the other mega trend that is relevant to experimental chemistry is robotics, and not everyone appreciates this. The cost of industry robotics has declined really dramatically in the last 20 years, and it's continuing to decline. So there was a time when a robot cost more than an NMR. Now it's very much the other way around, and these robots are getting cheaper and cheaper. And chemistry robots, the kind of robots you buy from companies like ChemSpeed, those robots have remained static in price, but industry robots have got cheaper and cheaper because it's a bigger market, and robotics serves a much larger market than research or chemistry. So it scales and will scale more, which really, it was partly for economic reasons that prompted us to build this robot chemist that I'll talk about in a minute, because the hardware was getting cheaper. Although it looks exotic in a chemistry lab, it's actually considerably less expensive than many of the instruments in a chemistry lab nowadays. But before I talk about that, I just want to say something about materials design, and this picks up on Ram Seshadri's talk. You know, we're very interested in a priori or de novo materials design, computational materials design, and we've been doing that for a long time, crystal structure prediction, and I'm a very big believer in this, first principles design, not using AI, but using computational models. And here's one example where we made some porous frameworks. These are not MOFs, but related to MOFs, molecular crystals. And we have some great MOF talks this afternoon from Mohammed and Omar. And these were designed in a computer. But these are crystalline materials, and you can actually, in this case, capture everything pretty much from an atomistic model, in this case. But that's kind of the exception, not the rule. And if you take more complex materials, or even worse, devices, we can't design photocatalysts, complex, heterogeneous photocatalysts from the atoms up. They're multi-length scale complexity, two semiconductors, for example, coupled with a redox system, with metal catalysts on the surface. They are beyond bottom-up atomistic design. A battery, I think it's obvious that you can't entirely design a battery from atomistic principles. And some years ago, when we first started to work on crystal structure and prediction, Jean-Marie Tarascon, who's one of the leading battery researchers in the world, I showed him some of our work on CSP. And he's in my office in Liverpool, and he said, yeah, your models, they're very nice, but for a battery, no. and he's right, of course. We cannot predict a battery from first principles in a computer, but you can predict parts of it, and you can calculate things which are relevant to the function, of course. But the whole device is irreducibly complex, and maybe always will be. I don't know if it will ever be possible to do exascale computing, prediction of a battery in a computer. But I'm going to talk today more about heterogeneous catalysis, which is complex enough. So it's too complex for this kind of a priori design. And this point was made yesterday by Ram, really, and it was made in this article by Tony and Ram and Fred Woodall. It was said yesterday. Actually, most materials that are used in functional commercial context, they weren't really designed. They were repurposed or inspired by something else. But that's not to say it's not good to try, and that's certainly true today. So at some level, our program in Liverpool is attempting to bridge those two things at some level between discovery and design. And there's a lot of interesting stuff in the middle, we believe. So this is the robot chemist, so-called. So it's a mobile robot. We didn't build the robot. This is a commercial system that is used in automotive manufacturing and other environments. And I won't go through all the details, but we managed to build a workflow where it could do the solid addition, the liquid addition, the photocatalysis, and the function measurement, which in this case is the amount of hydrogen produced in the photocatalytic reaction. And it's completely autonomous, works by itself. This is the chemistry. I don't propose to go much through the chemistry, but suffice to say we had, in this example, in 2020, 10 variables, and if you take all of the combinatorial or factorial combinations, it's about 100 million possible combinations. So it's a big space. You don't need very many variables to get up to 100 million permutations, though I'll come back to that later. And we had various hypotheses about why, for example, we were adding dyes to sensitize the catalyst, we believed, rather like a dye-sensitized solar cell. As you'll see, that didn't work, but the idea was to photosensitize the polymer semiconductor, and Christine talked about conjugated polymers yesterday. That's a conjugated polymer, dibenzosulfone semiconductor. And here's the experiment, and I've shown this video too many times now, but the robot works around the clock, measuring the hydrogen production, and it optimizes the hydrogen production. And in this particular case, it worked for 8 days in a row and did 700 experiments. And before we built this, we were doing 1 experiment a day. So it's at least 100 times faster. Actually, it's faster than that because the reasoning time is 0, basically. It makes a batch, measures it, and decides what to do next, effectively instantly. So it's very fast. And we got to compositions, catalyst compositions that were sort of 6 times higher, 7 times higher than where we started. And we used this method called Bayesian optimization, which is a very popular method for optimizing problems in high-dimensional space. Not only chemistry, in fact, originally it was used in stock market portfolios, other things. Recently has been used for multivariate chemistry. And it's very effective for dimensions up to 10, 15, 20 dimensions or so. But it's got a huge limitation, is it doesn't have any domain knowledge. It's just treating the chemistry as numbers. It could be a cocktail recipe or a cake mixture for all that the algorithm knows. There's no chemistry in it. And just to kind of give the example, I mentioned we used dyes in the experiment, and you can see here, as you go from batch 1 to 2 to 3 to 4, you see lots of colors. By batch 11 or 12, there are no dyes anymore. The algorithm has deselected the dyes. It's found that the dyes are not correlating with catalytic activity. But in no sense does the algorithm learn that the dyes are bad as a class. It simply deprioritizes 3 variables that happen to be dyes. So if you imagine you had 100 dyes, then it would go through every single one singly and learn that variable 1, 2, 3, 4, 5, and so on is negative. That becomes hugely inefficient. And if you make the number of dimensions bigger, that's just never going to work, because essentially the robot has no understanding of the chemistry. It doesn't understand that a solvent is a solvent or a base is a base, and so on. So that's not a good idea. It works in these kind of spaces of 10 variables or so, but it's actually inherently very inefficient. It's like creating the sort of world's stupidest but keenest chemist. It doesn't understand any chemistry, but it's going to just try really, really hard. So our initial approach to solve that was to put in the human chemistry ideas. So to inject the knowledge into the Bayesian methods, and we built this method called HypeBO, hypothesis-led Bayesian optimization, where we could inject the human hypotheses from a team. I won't talk about this in any detail, but we did a kind of fake experiment here where we set up an artificial team with, not a very good team actually, with mostly bad ideas and a small number of good ones. And we sort of tested this in silico. But we built this algorithm so that, without going through the technical details too much, it can select the good hypotheses and drop the bad ones. So, for example, one of the few good hypotheses is dyes are bad as a class. And you can see that that hypothesis is retained throughout the iterative optimization. But there's another hypothesis, I won't go into the chemistry too much, it's essentially partially correct. It's correct up to a point. And you can see that that hypothesis is used 3 times, but then it's dropped. So this is essentially having the best of both worlds, and you could have a team of 200 researchers, and of course these things cost experiments, but in time the good ideas propagate and the bad ones don't, in a sort of Darwinian way. But this too has some limitations. For one thing, all the hypotheses are put in at the beginning of the experiment, not during the experiment. So it's not active reasoning. It's like we put in our ideas and then we press run, which if you're doing chemistry or you know nothing, that's limiting, of course. You want to put your ideas in the middle of the experiment. Nevertheless, even with this team, which is essentially bad, it does better than Bayesian optimization by itself. The blue curve is the fake human team, and this is the Bayesian optimization. So even when most of the ideas are wrong, it's still outperforming no ideas at all, which is encouraging. But you can see where this might break down if you really start to automate things, because let's say you're doing 100 experiments a day, and we've got some systems now that can do this. I'm not going to be getting up at 4 a.m. to type my hypotheses into the machine. So there's a sort of mismatch between the experimental throughput and the human ability to create hypotheses. In fact, there's not really much point in building very, very fast automation if you're just left waiting for the human ideas, because then the ideas just become the bottleneck. So inevitably, we started to look at large language models, and initially, because when we started this, large language models were fairly limited. So we made a kind of hybrid system of the LLM with Bayesian optimization, because we didn't think it would be a good idea to use the LLM alone. And the way it works is in a very simple sense. There's a trust score, which means that while the Bayesian sampling is doing well, it will continue. And then when the LLM sampling is doing well, it will continue, but it can oscillate back and forth. Our idea here was when the LLM starts to hallucinate or form ideas that don't make any sense, then it will revert back to the Bayesian sampling. And there's a middle regime, which I won't talk about. And that worked pretty well, actually, in fact. In fact, this hybrid system outperformed this human reasoning because it is actively reasoning throughout the experiment. But as you can see, in 2024, when we did this, we also tried the LLM only, without the Bayesian method, and it was considerably worse. It actually did okay initially, but then it plateaus. That reflects the large language models available in 2023, 2024, which were comparatively crude. So the hybrid system did much better than the LLM alone in 2024. But that was here. There's been this sort of frenetic activity in large language models. Since then, this is some pseudo-intelligence score. I don't really put too much faith in this. But there's certainly been an evolution in these models, and these new frontier models. They're very different to the models available just 2 years ago. And of course, there's been an enormous amount of hyperbole here. So OpenAI claimed last year that GPT reached PhD level. I mean, I wouldn't agree with that. I don't even really think it makes sense necessarily to compare these things like with like, human intelligence and machine intelligence. Certainly, you can find examples where GPT-5 does not have PhD level intelligence. There have even been these plots which give these things an IQ score by doing standardized IQ tests. This is where we are in 2024. Clearly, we didn't want a model with an IQ of 65 running a lab. So if these numbers mean anything, that's not very encouraging. But as I said, this area has evolved, and the reasoning capability of these models are now much, much stronger. So recently, we were testing the new models, or newer models, again in this hybrid BO LLM setup, where the LLM effectively learns from the Bayesian optimization points, and the points from the LLM inform the Bayesian optimization. It oscillates back and forth. But what we noticed really was for some problems, the Bayesian methods now seem to be slowing it down. Effectively, the LLM is doing all the work. So recently, we've started to look at LLM-only optimizations. And it looks like this. So here's an example where we've done 150 experiments, and each one of these points is a hypothesis produced by the LLM, and they're all different. And it's a batch size of 1 in this case, so 1 experiment, rebuild the hypothesis, and so on. And it can much more effectively get to high catalytic rates than the LLM BO hybrid. So this is autonomous reasoning. This is an LLM reasoning point by point. And it looks like this. So you've got the robot, you've got the measurements, and then you've got these evolving hypotheses. And if you can do, 50 experiments a day, it takes 3 days to go through these 150 hypotheses. It's going too fast for you to read it. This is pretty different to human thinking, right? Nobody does an experiment and 30 minutes later builds a hypothesis and does another one and another one. This is very different. And I'm not claiming that this is human-level intelligence. But there is a possibility that this kind of shallow reasoning, iterated again and again and again very quickly, might get to answers that we wouldn't get to with human reasoning. And of course, there are some problems which an LLM would fail utterly at. But for this kind of multi-dimensional optimization problem particularly, I think this is very strong. And there are lots of problems in materials research and chemistry research which are, to some extent, high-dimensional optimization problems. And I think in those sorts of problems, and actually this gets pretty boring, in fact, to form hundreds of hypotheses again, and not many students, and certainly not the supervisor, would have the patience to do that, right? So for some sorts of formulation tasks, I think these methods will be able to do things that humans not only can't do, they just wouldn't do. And they do, it's working in a different way. So it doesn't really make sense to compare it with human intelligence. It's something else, But it is a kind of reasoning. And it does much better than Bayesian optimization. And to say something about this sort of reasoning in a loop, one thing we didn't realize initially is, but we realize now, we were initially doing 10 or 20 experiments in a batch and then doing the next 20 and the next 20. Well, of course, largely speaking, historically, science hasn't been done that way. There are some areas where people do batches of experiment, but often you do one experiment, then you think about the results, and you do another one. And there's a good reason for that, is it's the most information-efficient way. Nobody goes into the lab and does 100 experiments, turns off their brain, and then says, oh, now I'll have a look at the data. Nobody does that. And there's a good reason for this, because we've done science in the past by reasoning, not by building large models. And these methods are much more effective when the batch size is 1, and that makes sense, because every data point is considered. And there's been a lot made recently in this area of digital chemistry, or AI-driven chemistry, or whatever one calls it, about the combinatorial explosion in chemical space. And I think this came up in Ram's talk as well. If you have 200 elements, then the number of permutations is 10 to the 200, therefore it's impossible to find anything. But of course that's not true. And there are several papers now talking about the combinatorial explosion. But of course there's also, you can think of a combinatorial implosion. So if you do, let's say, 100 consecutive experiments using a robot, or even not using a robot, if you can restrict the search space by half each time, so say, right, I'm going to take all these possible experiments, I'm going to reduce the search space by half every time. So you say, right, okay, I've decided now I'm going to use polar solvents, not non-polar solvents, and so on. Well, actually, over 100 iterations, 0.5 to the power of 100 is 10 to, 8 to the times 10 to the minus 31. So this power of iterative reasoning is extremely powerful, and it goes in the opposite direction to the combinatorial explosion. Which is why, of course, we have managed to produce materials historically in the world. We don't just swim in the periodic table. People have reasoned over iterations over a period of time. So I think there's an opportunity here, if you can greatly speed up that cycle, the reasoning cycle. In a sense, this is more similar to what we've always done. Measure, make measure, think, make measure, think. It's a little bit different from machine learning. And this is not a great analogy, but if you want to take a ship from London to New York, you don't build an excruciatingly detailed map of the sea in the locality of London and then extrapolate to New York. That is machine learning, essentially. You don't do that. You use GPS and a few simple rules, and if you use GPS and some simple, it's not very difficult actually to go from London to New York. But if you try to learn the space of all possible oceans, then it's very difficult. So I'm beginning to think that this machine learning extrapolation idea, which is the basis of many of the AI spin-outs that are coming out recently, is probably wrong, because the space is just too big. So whether it's done with robots or not, I think this reasoning paradigm, I believe, is going to outperform machine learning, large-scale machine learning, particularly from things like materials problems. Because I think the experimental space is simply too big, and you have to walk through it rather than try to learn it. It's a sort of basic question. We will see. But certainly we are focusing now really almost entirely on this closed-loop reasoning rather than trying to build large-scale machine learning models. This slide hasn't translated very well, but there are some limitations of LLMs. For one thing, they are somewhat trusting. So in this case, this is the optimization using the LLM only. Here we fed it our previous paper. As you might expect initially, it does much better because it's learning from the paper. But then interestingly, you get to the end of the 150 experiments, eventually the unprompted LLM alone wins. Well, why is that? This seems counterintuitive. You give it information, it should help the optimization get to the best value more quickly. And we tracked it down to really one sentence in our paper. So we wrote this paper 5 years ago. We had one sentence that said, sodium chloride has a small positive effect, but less so than the 4 selected components, and it was therefore deselected. And what we think is happening is the LLM understands that. In fact, we have this sort of optimization log in our software. In all cases, it sort of reiterates what was in the paper. But then it can't, or it doesn't, let that hypothesis go. And it turns out actually there are conditions involving salt that we didn't find in 2020, which are better. So I think the learning point there is these LLMs are probably too trusting, and they take, perhaps, they're getting better at literature searching, but that's a double-edged sword, because if you believe all of the literature, because a lot of literature is wrong, right? So if you believe all of the literature, that's going to be self-limiting. So that's something to think about. Maybe is addressable by better prompting, but it's certainly a problem, because in principle, giving more information should help. Another thing is that we've got some evidence that these LLMs are too conservative. So if you look at Bayesian optimization, it does a very explorative search, and it finds a lot of compositions with zero activity. And this means that actually the LLM outperforms the Bayesian method, ultimately. But there's a big diversity of points all the way through the optimization, even at the end. But if you look at the LLM, it's quite different. There aren't many zeros, actually. So it's optimizing, then it's kind of forming this sort of, it's essentially going to an optimum and homing in on the answer more quickly. And for some problems, that's a good thing. But at no point will the LLM ever say, well, what if all my assumptions are wrong? What if everything I'm assuming is wrong? It doesn't do that, because that's not how these LLMs are trained. So, for sort of optimization problems, quite powerful. If you want sort of breakthrough lateral thinking as paradigm shift, this is a different idea, it probably won't happen, at least not with the LLMs that exist today. And we've tried better prompting, like, think out of the box kind of prompting. But it's basically in the training, and you're fighting a sort of unwinnable battle. So there are hard limitations right now. And this has been said by many people, is these LLMs, they're not, I think, at this point very good at true creativity, at least not yet. And you can see that here. They're very conservative. But to bring it back to some chemistry here are some of the materials we've been working on, which we call non-metal organic frameworks. These are organic salt frameworks related to MOFs, using the reticular principle, and actually initially designed using crystal structure prediction. But we found recently we're now making these sort of NMOF materials. They're too complex to do crystal structure prediction. The calculations are just much too expensive. So we're running these CSP landscapes. They're quite big calculations. And once you start to use more complex building blocks or multiple building blocks, that is a kind of combinatorial explosion. So we can't afford to do CSP for some of the new systems we're looking at. So we've reverted again to experiments. And we're trying to automate this. So we built some ways to do very rapid crystallization in plates. We can now do X-ray diffraction, single crystal X-ray diffraction in microtiter plates, which is really a big thing for our program now. This is borrowing ideas to some extent from protein crystallography, but now in materials. And that can get you structures, or at least partial structures. But the thing that's been most enabling is we've built this thermal imaging device for sorption analysis for porous materials. And And what we do is we dose in a gas, and the porous materials light up from the heat of adsorption. This is actually the reverse. This is the endotherm of the desorption, so the porous samples are black, so they're getting cold because we're removing the gas. And you can do both. And this is really fast. We can do 100 samples in a plate. In fact, we could probably do 1,000 samples if we miniaturized the wells or something. And here's some unpublished data. So we've been making some pretty large libraries now of these NMOF materials. And there are more than 1,000 samples here in 11 plates. So the color coding is the heat, so the heat of adsorption of, in this case, CO2. And you can see a lot of materials are not porous. In fact, that whole plate, there's nothing in it which is porous. But you can see green is good here, but there's one that stands out, like 1 in 1,000. So this material had a delta T, that's a temperature change of nearly 4 degrees, which is much higher than everything else on this plate. And I can't show you the structure at the moment, and we haven't published this, but this is a stable porous framework. The XRD is very consistent, and you can do multiple sorption cycles. The CO2 uptake isn't huge. It's 1.5 millimoles per gram, so that's not particularly high. But the isosteric heat, or the enthalpy, is really unusually high, 42 kilojoules per mole. So it's really absorbing CO2 very strongly. And this wasn't designed at all. This is from taking a library of linkers and counterions and making the combinatorial array. And I can't show you the structure, but the structure is surprising. It doesn't even look porous, actually. So it must be dynamically porous in some way. But suffice to say, it has a very high heat absorption. And we've also managed to sort of build in a stability measure because we can take these plates, put them in an oven, reanalyze them, get the temperatures again. And if you've got something which has a very high heat and is stable for months in an oven, it's like accelerated testing. So this might be also a method for accelerated testing. This is for these organic molecular frameworks. It could totally work for MOFs or COFs or any porous material, zeolites. And now, to come back to the start of the talk, we're trying to apply this closed loop reasoning as well. At the moment, we're not doing that. We're just finding the green cells in the spreadsheet and fishing out the sample. But in the future, we hope to apply this closed loop machine reasoning. So just to finish, I don't think LLMs are going to replace us, but I do think they could be part of what you might think of as a hybrid intelligence where we're combining LLMs or similar tools with algorithms. Still important, I think, to have physics-based models, calculations to guide things, and of course human intelligence. But I think the balance of these things will depend a lot on the property or the problem in hand. Sometimes calculations can be very cheap, or sometimes they can be very expensive compared to the experiments. So the kind of balance between these things will shift. If you're doing natural product synthesis in organic chemistry, we can't at the moment do that with robots at all. So multi-step natural product synthesis, that's still a human activity, so there is no robotics. That's kind of perhaps an end point where not only is it one sample at a time, it might be one sample over like 3 PhDs. That's a sort of end point. But then we've got other examples where we can do hundreds of experiments per day, at which point there's so much data that the human reasoning just, you can't keep up. So I don't think there's a magic answer here, and the best answer will depend on the problem. But I do think these combination of techniques and what I would call hybrid intelligence is the future. And I was initially quite skeptical about LLMs. I was, because we worked with them early in their evolution, and they weren't very effective at all. But I'm beginning to change my mind now, and I think they have a place. Not to replace human intelligence, but I'm pretty sure they have a place. I think they might replace Bayesian optimization for a start. And this is my sort of estimate for the future. Niels Bohr said it's very hard to predict the future. But if you think about how much physical understanding we have and the cost of the experiments, it might look something like this. For very fast automated experiments, I think almost by definition we're going to use some kind of AI because human brain won't keep up. I mentioned natural product synthesis, that's probably up here, you know, very high cost of experiments. But I think a lot of it will be in the middle. Yeah, I think a lot of problems fall in the middle, where there will be parts which can be automated, parts which can be done using artificial intelligence, and parts which can't. And again, it's hard to predict the future, but I think this is probably the interesting zone. Right now, there aren't so many fully automated labs in the world. But to finish on that, you might ask the question, is this a trend or is this just some crazy stuff we're doing in Liverpool? Well, actually, it's definitely a trend. So since we published our paper 5 years ago, there are a lot of activities now using mobile robots. They're being used in pharma companies in China. That happened very quickly. Materials labs, there's a lab in KIST, which is an unmanned materials lab. I haven't visited it, but it uses a mobile robot to do materials research. There's a large activity being built in Toronto, which this artist's rendition has mobile robots. They're certainly going to use robots. But I just want to talk a little bit about this one. One of my former postdocs now is leading a part of this. It says $300 million invested. It's now, I think, more like $500 million. And Lin Zhang, who was my former colleague, shared 2 of his slides with me. This is what they've got as the artist's impression for their facility in Hefei at USTC in China. It won't look exactly like this, but it's going to be a huge building with huge numbers of robots. And they've already started this program, so this is a video that he shared with me. I don't read Chinese. Those who do will get more from this than I, but this is Hefei. They have a large robotics hub, and they're building spokes all over China with different types of robots, all connected into one system. And you see these videos appearing. There's a mobile robot there, another one there. It looks like some kind of James Bond movie, doesn't it? And this is happening, and they've got something like 100 robots connected in multiple sites. I forget how many sites. And this is a really large-scale program, tackling organic synthesis, materials chemistry, catalysis, porous materials, very wide range of things, actually. Very big investment. So, and they're also working with large language models and different types of AI. I mean, as yet, I think it's probably fair to say there's not a sort of game-changing material that's arisen from this program. I think they would accept that. But it only started in 2024, so, you know, it's pretty new. And the pace at which this is being developed is quite astounding, actually. It took us 5-6 years to build what they seem to have done 10 times in 12 months. It's quite amazing. And they have a very big team and very smart people, so this is one to watch, I am sure. Just like to thank my group. I mean, I've got a really great group. We've managed to do this partly because we've got people who are not just chemists. We've got robotics people. We've got some computer scientists in the group as well. So couldn't do it without those guys. Some of these problems go outside of chemistry. And thank you again for the invitation.